Hello there, and welcome to everyone joining us for this latest IoT Central webinar. I'm Clive Maxfield, everyone calls me Max, and I'll be your host. In addition to being a practicing engineer, I also act as a technology consultant, author, speaker, and educator. I'd like to start our webinar by thanking Edge Impulse for sponsoring today's event. Edge Impulse is a leading supporter of the IoT Central community, and we're grateful to have them as sponsors. Today's webinar is entitled Building Smart Health Wearables. Before we begin, I'd like to briefly review the format of today's proceedings. The event will be 1 hour long. We have 2 speakers who I'll introduce in just a moment, and this event is being recorded and will be available on iotcentral.io tomorrow. I'd also like to encourage you to provide questions throughout the presentation. I will be reviewing and presenting these questions on your behalf during the event. Now, I'm very pleased to introduce today's speakers. David Schwarz is a user success engineer at Edge Impulse. Joining David is Mark Easley, University Program Marketing Manager at Texas Instruments. So thank you both for joining us. Whenever you're ready, David, you can take it away.
Thank you so much. Let me share my screen. All right, welcome everyone. Thank you for attending today's webinar. I'm really excited to get started. And what we have today is a tutorial on building health wearables with Edge Impulse and our partner, Texas Instruments. So to give a bit of overview about Edge Impulse and who we are, what we do. We are an embedded machine learning platform, and we are free for all developers. We are enterprising to democratize machine learning across many new fields and use cases. Our goal is to make it as easy as possible for non-experts to design, build, test, and deploy machine learning algorithms to the edge. We'll talk a lot more about what that means in the coming slides, but for now, let's go into a bit of our community. Oh, sorry about that. The Edge Impulse community the Edge Impulse community supports over 50,000 developers, 30,000 projects, and thousands of enterprise customers. We provide technology that you can't get anywhere else, such as our state-of-the-art Eon compiler. And we'll get into a lot more about what this means, but the kind of high-level takeaway is that we're a trusted platform for developing machine learning algorithms, and we have that community support and knowledge base to help you get started from any field or in any application. So why are we here? Well, in embedded systems, a lot of sensor data gets discarded due to bandwidth, compute, or power constraints. Our current tools aren't well suited for deploying and running machine learning on embedded systems. And many AI projects face challenges in going to production due to difficulties with testing, deployment, and other factors. So what we provide through our platform are solutions to all of these. We'll make it easy to design machine learning algorithms that help you use sensor data more efficiently and in more intelligent ways. We support a whole breadth of MCUs, but most importantly, the TI CC1352 family of microcontrollers, which we'll be using today. In addition, again, we have a developer-focused community that has the knowledge base and skill set to help you design and deploy your projects. This gives a brief overview here of our workflow, which we'll be seeing live in the demo a little bit later. What we do is we provide ways for you to easily collect data live off a device and then train and test your algorithms, and then finally deploy them to devices like the TI CC1352 LaunchPad, which we'll be using today. So let's get a little bit of background on machine learning and what its goals are and what some use cases are specifically around healthcare wearables and as well as other fields. So The thing to keep in mind is that IoT devices these days have access to so much sensor data. Aboard a dev kit like this has microphones, accelerometers, and atmospheric sensors, and potentially even cameras that can be connected very easily to gain a lot of context and information about its environment. But what's missing in current programming paradigms is how do you actually map that to an intelligent output? How do you get your device to understand its environment and act in a smart way? Well, that's what machine learning can bring. So in many different fields, this is hugely important. Today, we're specifically going to be talking about the healthcare and wearables fields, but you can imagine across anything where there's sensor data available, where there's data and devices that are currently deployed today, there's the opportunity to upgrade and augment those devices with improved intelligence. Specifically focusing on healthcare wearables, this is the perfect market for machine learning augmentation. A lot of wearables today provide sensor data from a variety of sources, including accelerometer, temperature readings, heartbeat monitors, things like that. From this, though, these data sources are very noisy, they are very complex, and they are hard to process with traditional techniques. And as we'll see today, using Edge Impulse, we're able to synthesize complex events and accurately output what is going on in the real world. We currently work with a lot of, we currently work with a lot of health wearable customers already, and we have proven experience saving development time and improving accuracy for sleep and disease detection algorithms on real devices today. So now that I've given an overview of Edge Impulse, let me briefly walk through our partner for this webinar, Texas Instruments, and the dev kit we'll be using, and the benefits of the Texas Instruments platform and system in health wearables and in smart IoT devices. So the first thing is that the device we're going to be using today is the CC1352 dev kit. This dev kit is fully supported by Edge Impulse, meaning that you can develop a machine learning algorithm on this dev kit with no programming experience required. We chose to partner with TI and to use this dev kit because of its capability around sub-gigahertz wireless and low power operation. Sub-gigahertz is an exciting wireless technology, especially in the space of health wearables, because it offers a lot of advantages over other wireless protocols and allows for a lot of interesting use cases that wouldn't be possible otherwise. Some great examples. Sub-gigahertz has exceedingly long range and is exceedingly robust. It's not affected by wireless noise on commonly utilized 2.4 gigahertz bands from things such as Bluetooth and Wi-Fi. And it has great penetration through solid surfaces, meaning you will be able to maintain a connection through a large building with multiple walls, barriers, things like that. Additionally, it's extremely low power, especially with the Texas Instruments app implementation, as we'll see today. The power savings on this device are huge, and we can have a battery-powered device running in the field for years at a time. Similarly to machine learning, sub-gigahertz wireless capability has a lot of potential to augment and improve applications in many different fields. In medical systems, we can improve the reliability of our devices with that long range and robust connection we get from sub-gig connectivity. In industrial and smart home markets, we can use that range and use that noise tolerance in order to maintain networks that don't interfere with other wireless protocols. And the MCU we're using today, the CC1352P, is a fantastic platform for developing such sub-gigahertz applications. It's a ARM Cortex M3 processor with a suite of sensor peripherals, a radar, a radio, and a host of peripherals that are great for operation with embedded machine learning. It also supports a suite of wireless protocols from multiple sub-gigahertz networks, as well as BLE, Amazon Sidewalk, and the TI 15.4 stack. So going over the sub-gigahertz solutions in particular, there are different trade-offs and advantages to different protocols available. TI supports all of these through their SimpleLink SDK, and you'll be able to use any of them in your application. A few I wanted to highlight are dual band capability, where TI is able to augment sub-gigahertz stacks with Bluetooth operation, allowing these robust networks to communicate with devices like smartphones. So I'd like to jump into a live demo and spend the bulk of my time showing you all what Edge Impulse and TI are all about and how to actually live design a health wearable. But I'd first like to pause and give a few initial poll questions to the audience and kind of get some discussions here. So first, are you excited or curious about how to use machine learning? Hopefully you are. We'll be talking a lot in depth about how to use machine learning in the context of wearable devices today. And we'll really be focused again on the health sector, where we're trying to improve patients or users' well-being through the added intelligence of the device that we're creating. So let me give that a bit more time to, oh, there we go, to process. And I believe we have one more poll question coming in shortly. And so for a lot of you, you may have seen Edge Impulse before. We've done a lot of IoT Central webinars in the past. We love working with IoT Central. And if you're familiar with our platform, hopefully this is going to be a valuable workshop. We're going to go into depth on a lot of the kind of considerations, especially around data collection and model architecture that come into play. So we will definitely get into a lot of new beneficial information for those of you who are familiar. But hopefully if you haven't seen the platform before, we can still provide an overview of how everything works and show how easy it is to use our platform to design machine learning models and deploy them on TI's development kits. Fantastic, thanks so much. All right, so it looks like most of us are new to Edge Impulse, and that's great. That's really great information, actually. So I'll, from here, jump right into actually live doing the, showing you guys how everything works. And so the first place I would like to start is our homepage at edgeimpulse.com. Here, if you're new to the platform, you can sign up for free. And from here, you'll be able to start creating machine learning projects. But once you've created your account, I recommend we go through our docs page. And here we offer a comprehensive getting started guide. And we have a version specifically for the TI LaunchPad. When you're using this TI LaunchPad, you can follow the instructions here to install some dependencies and Edge Impulse tools. But once connected, we're going to move directly into the process of setting up our board. So I have a board here that I've configured exactly as described in this guide. And the first thing I want to do is download and update the Edge Impulse firmware on the board. So if we look here, in order to flash this initial firmware, we're just going to open the zip file, and then I'm running off of a Mac OS system. So I will just run the equivalent script, but we offer that across all platforms. And so here you'll see kind of the window of flashing the Edge Impulse TI firmware onto the device. But this firmware is really going to be for data collection. We're going to use this to interface with the Edge Impulse Web Studio. And we're going to later train and deploy a machine learning model to this device. And so with this first version of the firmware, it's going to kind of be how you get that data in the first place. So once this is complete, we are now going to be able to interface with this dev kit through the Edge Impulse CLI tools. So I'll stop here and jump into Studio to show everything in action. But if you're working through this on your own, we have all the tools here in our documentations page for you to design your own machine learning model. And we have a lot of different interesting applications, specifically around the TI LaunchPad. So you can read more about that in our docs page. But what I have here is a project that I've prepared, which is a fall detector that is designed to take this dev kit and when worn, say, in a pocket or as a wearable, be able to detect if the user falls. And we're specifically going to be trying to detect 4 different classes of operation. We're trying to determine if the user falls over, or if they're doing a more normal movement, such as sitting down in a chair or on a couch, that is normal, that shouldn't be cause for alarm. Besides that, we're also going to differentiate idle states where the device is not in use, and unknown movement types where the user is, say, walking around, just going through their day-to-day activities. Now, so how do we do this? So first, once you've created an account and gotten to a project, you'll see a dashboard just like this. Show here. This dashboard is kind of the home page for a project, and it'll walk you through the process of collecting data, designing an impulse, and then deploying it. In the project info, we can see statistics about the data that we've collected and about if we've made public versions of the project, where we can view that, and I'll show what that looks like in a little bit. Following the process of designing a machine learning model at Edge Impulse really boils down to just going through all of the different steps shown on this left pane. The first thing we're going to do is go to the devices page. From the devices page, you can connect new devices, and you can use these devices to record new data. In order to record new data, you're going to go to the CLI, and you're just going to run Edge Impulse daemon. This CLI daemon is now going to connect to the Texas Instruments board, and it is able to now stream data directly from the sensor straight to the Edge Impulse Studio. You can see that the board is shown here, and we're able to configure parameters around the sample length and set up to actually sample data live. So in this data acquisition tab, we're going to see a list of all of the different samples that we've collected. Here, I've collected a lot of data in advance of this so that we can show the model in training. But essentially, each of these is an event that we want to detect. So this corresponds to the accelerometer reading on the dev kit when a user falls. In contrast, this is kind of what the waveform looks like when the user is just performing normal operations like sitting down. And if we go to filtering our data, we can select different subsets of our data to get a better view of what's happening. Here's some other examples of the user sitting. And here's some longer captures of unknown movement types. So this is a user walking around, just performing day-to-day tasks where they are moving a lot. And we don't really care about what these tasks are. We just know that they're all kind of mapped to this unknown class. Now, in order to start sampling, once we've connected via the CLI to the Edge Impulse Studio, all we have to do is press this button. I'm going to collect a small amount of idle data, just showing this device lying on my desk, not being used. So let's set this to just collect 3 seconds, and let's start sampling. We can see here that the device is sampling, and we also can see the countdown here. And then once sampling is complete, it will upload the device to the studio automatically. the data here is listed, sorry, I'm filtering it out. The data here shows the latest captured sample. And here we can see this idle data, it's just static, there's no movement. This is kind of the simplest use case for collecting data. We additionally support a lot of other options. So not all the time do you want to be live collecting data off of the dev kit. Sometimes you have pre-existing data sets. Or sometimes you don't even have a dev kit or hardware platform decided on quite yet. For those cases, we still support data ingestion through Edge Impulse. We offer the ability to ingest data through your mobile phone or through your computer. We also have a very simple protocol for implementing data ingestion on your existing firmware via what we call the data forwarder. And we provide documentation and examples on how to add such functionality to existing firmware. If you're working from a large data set, you can either upload data from your personal computer or integrate with our cloud services in order to kind of transfer and manipulate data at scale. So with the data set collected, I'd like to kind of go over a few best practices and guidelines that come into play when you're collecting wearables data. Because there's a lot of nuance here, and there's a lot that can affect the performance of your machine learning model in practice. First, you'll see in the data pane this pie chart showing the distribution of the amount of time collected for each class. Now, what we'll see here is that there is a general balance of about the same amount of all of the different samples, with the notable exception that we've collected a lot less idle data. What happens here is that generally for neural networks, you want to provide an even distribution of all of the different types of samples and data types that you're going to be expecting to see. If you provide a very unbalanced view of this, the model will train to be much more sensitive to certain inputs than others. However, the kind of the nuance here is that the neural network might end up having trouble learning one classification type over another. And as we'll see when we go to our classification, this is exactly the case for this application. Learning to detect falls and learning to detect unknown movements are much more complex than detecting the case of the device is not moving, it's completely idle. And additionally, sitting down is a more controlled motion, and there's a lot less noise involved. So it was easier for the network to learn this as well. So in improving the accuracy of this model, I've taken extra data in the unknown and falling categories in order to improve the model's exposure to these more complicated scenarios. And so this is a very empirical process. When you're developing your machine learning model and collecting data, you want to have this tight loop where you're able to collect data from devices, train your model, see how it performs, and then from there collect more data in order to shore up areas where the model struggles. And so this is exactly what is being shown here. The next thing we want to do is make sure that we have a robust test data set. And this test data set is very important. So the training data is going to be synthesized by our Edge Impulse workflow in order to train a neural network to recognize the 4 events that we've chosen. However, it is very easy for a neural network to train to fit our data set specifically, this 17 minutes of sample data, rather than the motion that we're trying to detect generically. And so what we want to do is we want to store examples of the movements that we're trying to detect, preferably from real world use cases, where the model will never see this during training. And what this means is that when we test our model's performance against this data, we have a known benchmark that we can compare model performance against as we improve over time. So to do this, all you need to do is navigate to this test data tab at the top, and then you can collect new data just like you can for the training data set. In here, this data set since it isn't shown in training, it makes the most sense to actually show a balanced representation of the data. The neural network isn't being trained on the test set, so there's no need to show extra examples of the more complex behavior. We're really trying to identify here what the real world behavior of the model is going to act like. And for that reason, we need to have a representative data set maybe of the tasks and that you would experience when using the device. So I think that covers about all I wanted to talk about for data acquisition for now. And there's a bit more that we can go into, but I'd next like to go through the process of designing what we call an impulse, which is our solution for creating and architecting your own machine learning model that you'll later deploy to the device. So we have a lot of options and features available here, and I'll just walk through our choices both for this project and for some other considerations that might be useful for other applications. So the first thing we want to do when we are working with time series data, such as an accelerometer here, is we want to select a window size that we will capture a buffer of that length, and then we will run the neural network on the data captured in that buffer. The size of this is relatively important. The important thing to remember here is that we want to make sure the window size is larger than the event we're trying to detect. It's going to be very hard for our neural network to detect a person falling if it takes them 1500 milliseconds to fall, but we're only capturing a 700 millisecond window. So here I've set this to 4 milliseconds. That's going to be 400 samples per accelerometer axis. And that's going to give us a relatively wide view to detect if a fall occurred. Now, along with the window size, we have the window increase. The window increase can be thought of as how often you run your neural network on this 4-second buffer of data. So if this buffer was set to a very small value, we would run the neural network on a 4-second window. We would shift 650 milliseconds in time, and then we would collect the new most recent 4 seconds of captured data. And in cases where we want a model to be very energy efficient, the best way to do that is to determine how frequently we really need to run the model in order to capture the use case that we're looking for. Here, since we're capturing windows that are relatively fixed in time, and the event we're looking for, a person falling, is short compared to this 4,000 millisecond window, we can increment an entire frame each time. And this means we only need to run inference once every 4 seconds. It likewise means that the device's latency for detecting that something is wrong will be 4 seconds. In this use case, that is completely fine relative to kind of human response times to being alerted that there's a problem and going to potentially check on the patient. But in other applications, that latency might be very high. So in those cases, it would make sense to lower the window increase. Next, Edge Impulse has a lot of DSP pre-processing blocks that we like to run on input data before we pass it to a neural network. We found through our research and development of working with many different companies and implementing machine learning on embedded devices that it can be very, very efficient to pre-process the data before it's sent to a neural network. So some examples of what this looks like. We could potentially create a spectrogram, a 2D image of the sensor data and its frequency content. Once we have that frequency content, we could run an image recognition algorithm on our device that can differentiate between different audio signatures. For simple motions, such as detecting a sinusoidal wave, we can run spectral analysis, which runs a simple FFT to extract the frequency content of the entire window of the signal and then classify based on that. And we offer a lot of other dedicated blocks that can be very useful for different specific applications, such as audio or voice. However, here, we're working with a very specific thing. We're looking for, as shown in this data acquisition view, an event that occurs at a specific point in time and has a lot of time series variation, noise, and content as the event occurs, as the user is moving very quickly. And so as a result, it doesn't really make much sense to run some of these pre-processing blocks for this specific application. So what we also allow is what we call just raw data, where we take that buffer, that window that we collected, and we send that directly to the device, to the neural network. So if I show here, this is kind of the raw data view for for this block. And this isn't doing any modification onto the data that we collected, except potentially we can scale the axis of that data. Here we're just going to leave it as it was collected. And once we have this, we're now ready to send that data to an actual neural network. So Edge Impulse supports multiple different types of neural networks and machine learning blocks. The first one, which we'll be using today, and our most commonly utilized option, is called a classification network. This means that we're mapping the input to a discrete set of output classifications. For instance, here, whether the user is falling, sitting down, if the device is idle, or if they're doing some other activity. And it's really interesting with classifications, because it can be any set of discrete options. There's a lot, it's really only up to what your use case needs for your application and what problem you're trying to solve with these are. So it can be completely arbitrary, the kind of buckets and containers that you sort your input data into. A great example of this is here. I'm delineating two very specific motions, falling and sitting down. But then I'm putting any other movement that the user would normally perform into this unknown category. And that's completely fine for a neural network, but that sort of processing might be really difficult to do in other paradigms, where if you're looking at thresholds or doing decision tree based algorithms, it can be very difficult to kind of focus in on the exact types of events that you want. And so that's one big advantage of classification networks. The next thing I'll talk about is what we call regression neural networks. Now, what these do is, rather than output a discrete set of classifications, they output a single continuous value. And you can imagine that this is quite different in its use cases from a discrete set of labels. But the neural network technology behind it is exactly the same. And that's really cool. That means that we can teach devices to do things such as estimate, say, a quality of the user's health, such as maybe their blood O2 levels, give a percentage to the quality of their sleep, or track something such as their fitness level or aerobic breathing level based on other types of sensors that we don't have present. So a great example of this is potentially detecting blood pressure based on, or inferring blood pressure based on heart rate, things like that. And so those are just some kind of high-level examples, but I wanted to make that distinctions where in certain use cases you're looking for that discrete set of outputs, and in other use cases you want that continuous value. You want that estimated rate of something or something like that. And then finally, a tool we often use in supplement to a neural network is what we call an anomaly detection block. These blocks are useful for determining if new input data is not representative of the data that you've collected in your data acquisition tab. What this means is that in a situation where a neural network is trained, say we train this neural network to only detect falling and a person sitting down, those idle and unknown cases would now likely be classified as anomalies. And we could alert the developer or user that, hey, this neural network is in a situation that it likely hasn't been trained to handle well. And from that, we can do things like try to collect more data off of that anomaly event, or run some special procedure that happens when that unfamiliar territory gets entered. And so we generally see, though, that the classification can be very effective in cases where you're able to collect data of all of the different event types that you're looking at. So really this is for when you aren't able to collect data about a certain type of event. In a health wearable, say it's from a life-threatening situation that doesn't happen very often, that isn't something that you can just go out and get data on. Here though, we're working with relatively straightforward things. If a person falls or sitting down, we can get data for all of those. And so as a result, we aren't using this here, but it's just something to consider in cases where you might be thinking, okay, I have this data, but I can immediately think of cases that could occur, and I have no idea how I could collect data that's representative of those events. So with that, here again, we've just selected a discrete classifier to classify these 4 outputs. And we're going to be saving the impulse to finalize our settings. From here, all we need to do is generate features from our data acquisition. And in this case, the feature is just that buffer that we captured that's 4 seconds long. And so we're going to be slicing all of that data we collected up off of the devices into 4-second windows. And we're then going to be showing here in our tool a visualization that tries to approximate how alike and similar the different data in our data set is. And this can be really helpful. Here we can see that there are a lot of different categories of this data set that are very separate from one another. Certain types of falling events are grouped together. Certain types of idle events, as we expect, it's the device isn't moving, are very close together. And then there's this more complicated block here that shows that there are events with some overlap. Sitting down might have similar features to falling, for instance, because you're both moving down on that y-axis. And so that's something where in traditional processing, this uses a non-machine learning based approach to do this kind of similarity estimate. And in doing so, we can get an idea of how difficult it will be to parse this data. If we had a data set where one label was in one corner of this and the other label was completely over here, you could write some manual code that would just linearly classify between those two. You wouldn't need the neural network. But because we're seeing a more complicated case, especially with this block of samples over here, it kind of gives us an intuition that we are going to need some more advanced processing. And it also gives us a kind of intuitive understanding of how difficult it's going to be to train our neural network. And that's not to say that it will be extremely difficult for a case such as this. It actually doesn't turn out to be that hard for the neural network to learn to make this distinction, as we'll see in just a bit. But it's just something that's important to mention. And then finally, we also in our tool provide on-device performance for the TI dev kit that we've connected on how much RAM and how much processing time this is going to take. The RAM usage comes from our 4-second window of collecting data before we run processing. But because we're not actually doing any DSP, it doesn't cost us any computation time, which is great. In other cases, such as running a spectrogram, this might take a lot longer. So now that we have our data, let's talk about the neural network. So this is our UI for architecting your own neural network. Now, if you have never done embedded machine learning or machine learning development before, this might look completely unfamiliar. And for all our projects, we provide presets, sensible presets for what a good starting point might be for a machine learning model. Here, I've created a specific architecture that I found to be very effective for detecting the types of events that we're looking for here, fall detection, where we're running convolutional neural network layers in order to filter and capture features from the time series window that we've collected, and then classify it as we go through the different layers. And so, again, if you're a new user, you can refer to our kind of getting started models in our tutorials, which we have available on our docs page. But if you're a more advanced user, you might get to this point and say, okay, but I just want to write Python code or actually develop in the framework I'm more familiar with. And so for advanced users, we also offer what we call expert mode, where you can just design your model using Keras. Anything supported by Keras is available here. And doing so, you can do a lot of cool things that go kind of outside the bounds of normal machine learning within our platform. So we had one of our engineers do an example of designing an RC car kind of automatic driving model. And they were able to do that just by grabbing a known effective model from some research that was written in Keras and imported into our platform. And this can be really powerful around health too. There's a lot of research in using machine learning to augment and improve health wearables. And so you can leverage that with us. All you need to do is switch to expert mode, go to some publication, some open source model that's been shown to be effective in a certain application, and you can run that with us. And so for this situation, we are just operating from a custom model that I've designed. And I'm going to start training this model just so we can kind of see the training live. But I don't want to take, this might take a few minutes. And so while this is training, and we can see it's running through pretty quickly, I'm going to go through and kind of go to the next steps in the public copy of this project. So here we can see the already trained model. And we can see that we've been able to achieve pretty high accuracy. And this is an exact copy of what I'm running here. And we'll be able to see this in a second. Once we have this model trained though, like I mentioned earlier, this just shows its accuracy at learning the training data set. We actually want to verify that this model is effective in the real world on data that it's never seen before. And so to do that, we're going to utilize that test data set in this model testing view. I've kind of spoiled the result here where the accuracy is pretty good, maybe a little bit worse than the training data set. But just to kind of show, oh, sorry, I will switch back to this one. So the metrics have kind of changed here, unfortunately. I believe that this is just from, maybe from I think I left the extra data in that I was collecting earlier. But I'll just kind of go through the testing view here. Another thing to note is this public project and the exact data impulse and training that was used here is available at this link for any of y'all. And I'll share that link at the end of our slide deck. But you can take this project, play around with it, and try different things out as you want to. And this architecture is also generalizable across a few different applications. There are other similar events to detecting user falling that this might be effective for. So looking through here, we can now go through our model testing, and we can look at samples that maybe were misclassified. And we can try and get an idea of why this data was difficult for the neural network to detect. So we see the sample that we are classifying. We see the result here. And in this result, we see that the neural network is completely certain that this isn't a fall, that this is an unknown model. And we can kind of get an analysis of why that was the case by looking at this 3D view. We can see this is part of this cluster up here, which has data from 3 different classes: unknown, sitting down, and falling. And so from this, this is great information for future revisions of our model. We might want to take this sample, add it to the training set, and take other samples with similar parameters to try in our test set and try to improve the results. Or we might want to leave this in the test set as a benchmark and try and collect similar samples or test different model architectures that perform better for samples like these. However, for the cases of this demonstration, low 90s percentile is okay here. And so from here, in addition to kind of what we showed in the model testing and acquisition about collecting more data, we also want to be able to always get back to a version of the project that we got to. So as I saw here, at some point I've changed something in this project that's affecting accuracy very badly. And so I want to fix that. So at any point, I can just reload the project to this exact state. And in doing so, I'll be able to kind of lock in the performance that I was able to achieve there and generalize it for future versions. So as shown here, if I make a mistake or if I make a change to my model architecture that causes problems, I can go back and restore kind of my prior performance. Finally, we're going to get to deployment. So here is where the TI board comes in. So once you have your machine learning model trained, we support directly deploying this device to the TI LaunchPad just by selecting the binary here. Once you've selected it, we're going to provide you live estimates of the latency, RAM, and flash usage for your specific device. And we'll let it see here once it runs. And then while we're here, I'll talk a little bit about our Eon compiler, because this option is maybe a little bit confusing otherwise. Yes. So here you can see with the Eon compiler, if I turn this off, the RAM and flash usage goes up quite a bit. And so what's happening here is our Eon compiler essentially compiles down the model architecture that we described here into a more efficient way than traditional Keras TensorFlow Lite-based models. And the advantage of this is that you save on memory. And this is something that we're really proud of. You know, the button is just, you just press the button and it works, but the technology behind it's really cool and it's really unique in the industry. And so from here, let me go to the public version of this so we can get the accurate version. We can just build the firmware. Let me go to the restored version of it. Sorry. We can just build the firmware. And so here, it's just going to build on my screen. And then we can flash it the same way that we did with that initial firmware that we downloaded from the docs page onto the device. I'll let that build for a second. And while that's building, I'll just show with the initial firmware what it looks like to run the machine learning model. So all you need to do is likewise with data ingestion. You'll just need to run edge impulse, run impulse, another one of our CLI commands. And this talks to the Texas Instruments device and tells it to start running inference and detecting the result. This model, again, is just the initial version that I flashed from our documentations page, so it's preloaded with a very basic model. But once we have our full firmware, we can do the exact same thing. I'll show that in a little bit, time permitting. So from here, let me hop back into our documentations page, and I'll just go through some final points. So once you've done this, you'll have a machine learning model that you've trained and tested on our platform, and you'll have deployed it on the LaunchPad. So now the question is, how do you integrate this with your existing firmware, your existing projects, or something new that you're starting that's going to do more than just print the result to the screen? Well, if you follow our documentation, we offer examples and guides for running your impulse locally using the TI LaunchPad. And the example and tutorial that we show here is fully compatible with TI's SimpleLink SDK. So anything that is already running on that framework or within that SDK can pull in our Edge Impulse library and can run inference. And this makes it really easy to add intelligence to existing projects. If you have the memory and flash and compute resources available on a deployed device, and that device can receive over-the-air updates or be updated in the field in some other way, you could potentially train a model, test that it works well, and actually deploy it to the field live with your existing firmware. And that's a really cool capability that serves to, you can add intelligence to existing devices where you need it. And you can also avoid kind of having to redeploy or make a new version of a product that's kind of machine learning enabled. And that's really exciting. So with that, I think that's about all I want to cover in terms of the live demo for now. I want to make sure we get back to the last few questions and polls before we run out of time. So let me hop back to the keynote. And I think we have one more round of poll questions that we can go through. And so, yeah, I'd like to have everyone kind of think about, in whatever application, whatever field you're working in, how adding intelligence to either an existing device or a new device with a similar application might be useful. So in this case, we're covering a health wearable where or detecting a more complex event than you could detect with traditional processing. But maybe in other wearables, things like detecting quality of sleep, like I mentioned, detecting disease, these things in the health field are all exciting opportunities for machine learning. And so if you're unsure on that, just before we go to the next one, if you're unsure on that, one thing we offer at the Edge Impulse website is we have, both from our community and from developers like me, a lot of demos and blogs and tutorial videos, all kinds of stuff like that, showing all sorts of really interesting and unique use cases for machine learning. There are a lot of really, really great examples from our community, just other people who are kind of experimenting with ML and sharing it with all of us. And so if you head to our website, to our blog, we'll highlight a lot of those, and that might be a good way to kind of get some ideas and get some additional kind of examples of where machine learning is useful. And so for the TI board, I'd like to reiterate kind of where this comes in. So first, we've made this fully supported by our platform. You can, with no prior programming experience, buy this dev kit and start programming with and start developing machine learning models. Once you go beyond that, we also offer support and integration with the SimpleLink SDK. And the device itself is really powerful for sub-gigahertz wireless communication. And as mentioned, that has a lot of advantages. It can, it has a superior range and robustness over traditional 2.4 gigahertz protocols like Bluetooth and Wi-Fi. And that allows it to operate in conditions where resilience and low power and reliability is much more important. And I think the health sphere is a great example of this. Fantastic. So with that through, I'd like to, as a last page, point you once again to our website at edgeimpulse.com. You can get all of the documentation and information about getting started with our platform. And then I'd also like to point everyone to the fall detector project that I shared today. That public version is linked here. The link and slides will be available after the webinar for anyone who wants to access it. And then on the TI side, TI offers a lot of great resources for getting started with their LaunchPads. All of their different supported wireless stacks. They have a huge array of different sensor boards that you can add on to this kit to connect different things like atmospheric sensors, audio, things like that. And so that can be a really cool tool with Edge Impulse as well. So again, highly recommend after this, grab these slides and kind of make use of these resources if you're interested in starting on a TI-based project. And that's my final slide. From there, I'll hand it back over to Max for a Q&A. And yeah.
Well, thank you, David. Very interesting. Amazing that 88% of people are planning on using this sort of technology in the next project. It's only a few years ago that no one had even heard about AI and ML. So now it's time for our question and answer session. We've got some excellent questions have come in throughout the course of the presentation. And also I encourage everyone to keep on sending any last minute questions in while we still have time. First question, and hopefully Mark's going to join us. Was all of this demo developed with the free layer of Edge Impulse?
Yeah, so that's a great question. So to kind of give an overview of what that free version, I mentioned earlier that any developer can sign up for free. The way our platform works is that if you sign up for a community account, you get access to 20 minutes of training time for a project, and you get access to up to 4 MB of data storage. And so for a project like this, I only needed to collect 17, 18 minutes of data, which is far, far below 4 MB. And I also only needed to train for, as we were doing it live, about a minute, maybe 2 minutes. And so in certain cases, you might need more than just a minute of training, but most of our use cases, especially around time series data like accelerometers, is completely accessible from our free tier 20 minutes of training time.
Okay, cool. We've got someone here saying, if I don't have the physical device, how can I proceed? Is there any platform that provides data from simulated devices?
Yeah, so there's a few ways you can go about that. The first way I would suggest is that kind of the best multifunctional sensor everyone has now is a cell phone. And so I didn't show this in the example, but in our tool, if you go to the data acquisition view and select a mobile phone, you'll be prompted with a QR code. All you have to do is scan that QR code and go to the website, and your phone will automatically stream its accelerometer data straight into Studio. And so you can use that, and it's really interesting. You can use those different the different accelerometer data from your phone from the TI device, and you can still train a model that's going to be very accurate and very effective. Beyond that, if you're working from simulated data, what we generally see is that you'll either have a data source that's a pre-existing data set, or you'll be working from some other sensor type. And what we do is we support uploading both CSV files of any type of data stream, as well as implementing, as I mentioned, our data forwarder. And so with the data forwarder, you could, in theory, simulate some output. All you have to do is over some serial port, provide a comma delimited string of sensor values. And our Edge Impulse data forwarder tool can process that. So I think we should be able to support that in a few different ways, as I discussed.
Okay, cool. What sensors are best suited for tiny ML?
So for TinyML, what we see is that, and that's a great question, by the way. We see there's a lot of interest right now and a lot of familiarity with audio. So you might be familiar with smart home systems such as, a device that can turn on the lights by you asking it to, or things like that. And the interesting thing with that is that audio kind of only scratches the surface of what's available. So we see a lot of use from accelerometer-based data, temperature and atmospheric data, LiDAR and radar-based sensors for detecting motion and things like that. And so really, I think the best sensor is anything that you can get a time series, data stream from. And the only thing is that the more complex that output is, the harder it is to kind of discern what's going on through traditional methods, the better a fit it is for AI. And then finally, the other thing is that to think about is that with the Edge Impulse platform, we can combine an arbitrary number of sensors and sensor axes. So the best sensor might be combining some accelerometer data with some temperature data and other tools. And so with both the kind of suite of sensor board add-ons that TI provides for this LaunchPad, as well as with the kind of Edge Impulse platform, it's really easy to do that.
Okay, and we've got one here that's TI specific. Is it possible to use this ML firmware on TI's MSP430 hardware?
I can actually answer that.
Oh yeah, go for it, David.
Yeah, so yes, it is. And we actually have an existing example of this that we've already posted, kind of as I mentioned, one of those community blog posts. So while the MSP430, won't necessarily work with that pre-built binary firmware, the Edge Impulse library is absolutely can be run. And like I said, we have an example for that. I'll grab this and we can share that link in the chat.
Okay, and we've got one here. Will this demo be available for export to TI Code Composer Studio?
Yes. So the library itself is just a self-contained C, C++ zip file that you can export. And we've provided examples in that running your impulse locally tutorial that are provided on how to use that with Simple. Now, in that example, we are compiling with a makefile through GCC, but there's no reason that you can't integrate our library through a code composer project. All you need to do is include the library and then add the header files shown in the Edge Impulse library in order to kind of be able to access that and run inference. And so it definitely will work and will export into Code Composer Studio.
Okay, so we are on the hour. The demo did run a little bit long, but yeah, we can stay a bit longer. I know it's unfortunate for people who've already booked the time and have fixed schedules, but maybe we could just race through some questions. So that's a way of encouraging concise answers, I suppose. Will a complex model affect battery consumption?
Absolutely. So the way to think about this is that when we're running inference on the model, we are, for however long that in the Edge Impulse Studio it says that it's going to take 7 milliseconds to run inference, you're running generally at the highest energy mode on a given microcontroller. And that, of course, is going to vary from microcontroller to microcontroller. But if you're working with something like TI that's very efficient and low power, even in that higher energy mode, you're going to kind of see savings there. But you can also calculate, get an actual energy cost of, hey, how much energy did it require to run that model based on the kind of full power mode consumption of a kit like the TI board, and then the inferencing time. And so running a more complex model with more complicated, potentially DSP preprocessing definitely can take a lot more time. And so because of that, that's where that kind of consideration goes with that I mentioned during the demo of how often do I need to run this neural network in order to get kind of the use case that I want, and how much pre-processing and kind of complexity do I want to really add to this model? Can I minimize the design of the model and still get the accuracy that I want? Maybe it's possible in the example I was showing before, if I used a model with twice the number of neurons to improve the accuracy from 92 to 95% on my test data set. But maybe that's not worth it given the constraints of my device. And so it's just a use case by use case situation. Oh, and I'll add one more thing on that actually. The final thing though is generally the most expensive thing a microcontroller can do is send some data over wireless. And so a lot of times you'll actually get energy savings from implementing a complex neural network just because you can send data only when an event occurs or something like that.
Okay, we've got two questions that are very similar here. One says, is it possible to run 2ML models with some delay in microcontrollers, model 1 with accelerometer data, model 2 with audio data? And another one, can we deploy more than one model for 2 different functionalities on the same microcontroller?
Absolutely. So we support both with an Edge Impulse. I kind of mentioned this a little bit, but didn't show it, where that anomaly detection block, we normally use it as a supplement for, we'll have a neural network, but then we'll also be running anomaly detection. And the same applies for running multiple neural networks. And so you can, within a single project, have 2 different neural networks, train them for different things, and then run them on the device. On device, it'll actually happen one at a time, but it's as if they're kind of one unified block. The only limit to that is the output classes. So in that case, you might be looking at, okay, I want a model that parses my accelerometer data, and then I want another one that does this other type of sensor. But if I'm trying to detect 2 completely different things, all you have to do is include the Edge Impulse library and model files multiple times. There's a few duplicate dependencies you need to remove in our SDK, but there's not that many. And from there, you can just actually run 2 instances of Edge Impulse on the device. It's completely possible.
Okay, excellent. So we're spoiled for questions, to be honest with you. So but we'll deal with that in a moment. Can I use inputs previously? Can I input previously collected data, like in CSV format, on Edge Impulse to train my tiny ML model?
Absolutely. So we support CSV as an input type, and I'll be sharing, we'll share a link in the chat shortly with some kind of an overview of what our CSV format looks like and what the process is for collecting it.
Quick one. Is a floating point unit required to use Edge Impulse?
So no, a floating point unit is not required. And the way this works is that when we go to deploy a model on device, we can do what we call quantization, where we map the floating point range of values that we use during training to an int8. So you'll get 255 discrete values. And in cases where, and this is a really common optimization technique for embedded neural networks. And when you do this, this means that when you're actually running inference on device, you don't necessarily need an FPU. Now, there are some things in our SDK around data ingestion that will require a floating point type, but the overhead for collecting that can be relatively low, such that you could, we operate on M0 cores that don't necessarily have an FPU, but can still do software implemented floating point for kind of some light loads, but then we're using that quantized int8 for all of the processor intensive stuff.
Okay, there's some questions here that are just too long to cover in a short answer. So we'll stick with the short ones. What are the minimum hardware requirements in terms of CPU speed, clock speed, I guess, and RAM to use Edge Impulse?
Yeah, so there really aren't any minimum requirements around CPU speed. It's really use case specific, you know, what model you're running and how complex it is versus the processor you're running it on. In terms of RAM though, the minimal RAM overhead of our SDK with like a very tiny model with only a few neurons, about the smallest you could get away with, is about 1.2K of RAM usage. And so that's kind of the minimum overhead that I would say you need to run the smallest possible network. And it obviously goes up from there as you're working with more complicated networks. Generally, our framework is you need 1 to 10K of RAM for these accelerometer time series data, and then you need like 10 to 50 for kind of more advanced cases with higher frequency sensors.
Okay, we have gone over, so I think we've got time for just one more question. But which one should it be? Is it possible to differentiate between abnormal data and garbage data when training the model?
So interesting. That's an interesting question. So I think the distinction there would be two distinctions to make. The first is, are you working in an environment where you're labeling that abnormal data and you can recognize it? Or are you in a situation where you don't really have an understanding of what abnormal or normal is? If you're working from that view of, okay, I know my abnormal case, I know my normal case, then you could create a model that has those two classes and then add anomaly detection onto the end to detect that kind of garbage output of like, oh, my values just make no sense whatsoever. And so I think that's the main thing, is you would need to be able to work in an environment where you can classify those normal and abnormal cases and then anomaly detect your way out of the kind of garbage.
Okay, excellent. And I should point out that our speakers have told me that you can feel free to contact them directly using the contact details shown on the screen. I'm sorry we didn't get to ask any questions for you, Mark.
No worries. Yeah, I appreciate everyone attending the session today. We're very excited at Texas Instruments to present these capabilities on one of our great devices here. So really look forward to hearing what you all will be doing with it in the future and implementing machine learning with TI technology. So thanks, everybody.
Okay, excellent. Well, I'd like to thank the audience for the questions and to the panel members for their insights. I should point out that I don't think I've ever seen more questions on one of these sessions. We've got way more than we could have answered in another hour or so. So for those of you who posted questions that weren't answered, we will be forwarding them to the members of the panel so they can follow up with you directly later. As a reminder, this recording will be available for on-demand viewing starting tomorrow, where it will be found on IoT Central at iotcentral.io. And this brings today's webinar to a close. I'd like to thank everyone for attending. Special thanks once again to Edge Impulse for their sponsorship, and especially to David and Mark for their presentation. Once again, this is Clive Maxfield, and I'm very pleased to have been your host for today's event. I look forward to seeing you all again on the next IoT Central webinar. And until then, from all of us here at IoT Central, we hope that everyone has a wonderful rest of the day.